All right, we're going to go back and we're going to talk about the tangent line. And in this class, over and over and over, I've talked about find the equation of the tangent line, correct? And that we've always needed two things, a point and slope. And we found the slope of that tangent line by taking the derivative. So let's say this x value right here is c. And this thing is f of x. And so there's a point right here called c comma f of c. And there's going to be a tangent line that's going to be touching that f of x at that point. And this tangent line has slope. And its slope is f prime of c. We should be all okay with that, correct? So the general form of a tangent line, and I'm going to write it a little bit differently, I'm going to write it in a functional form. And that means I'm going to input x into the equation of a tangent line. Everybody have that idea? Okay. And I'm going to use the equation of the tangent line, which is the slope, which is the derivative of f with c plugged into it, times x minus c plus f of c. So this is the point slope form that used to look like this. Is that making sense? This is algebra. This is, I guess you guys even called it Y1, I suppose. This is calculus. Are we okay with that? Now, there's going to be a point here. And right here, I'm going to have a value. And this value I'm going to call x. And so this point here is x comma f of x. And I'm going to want to know what f of x is. What it's equal to. Well, what I'm going to do is I'm going to plug that x in, and I'm going to plug it into the equation of the tangent line. And so this point right here is x comma y, the tangent line, with x plugged into it. So in other words, I'm going to let that value x into the tangent line approximate what f of x is. Why can I do that? Because they're pretty close together, correct? And the closer that x is to c, the closer that the tangent line is to the function. Can you see that? Like if I move it to here, I'll blow it up a little bit. Like if I move it to here, this f is f of x, this is y of x. They're really close. They're a pretty good estimate. All right, that's where I'm headed. That's using the tangent line. It's called linear approximation because I'm using a line to approximate. All right, so let's take a look at the notes. So that's kind of what I'm saying right here when I talk about linearizations, where I say the idea behind linear approximations is that it might be easy to calculate calculate the value of f of c for some c, but difficult to compute the value of f of x for some x near c. And I'm going to give you an example. Like, what's the square root of 16? 4. See how quickly you did that? What's the square root of 16.2? More difficult. 4 point something, right? It's a little bit tougher. So I'm going to define compute. I'm going to back this off some more. I'm going to define compute as a computation using your mind rather than a calculator. Because when you said the square root of 16, you came up with 4, you didn't need to go to your calculator. The same thing, if I say what's the square root of 100, more than likely, most of you will say 10, right? And for example, if f of x equals the square root of x, then f of 4 should be relatively easy to compute compared to 4.5. F of 4 is equal to 2. F of 4.5 would be difficult to compute. But before we figure out the f of 4.5, let's review a couple of points. Assume that f is differentiable. So that means I can take the derivative on f. How would you write the equation of the tangent line to f at c, comma f of c? To write an equation of a tangent line, Tegan, what two things do you need? You need a point, and you need slope. And so our point is going to be c, comma f of c, and our slope is going to be the derivative of f with c plugged into it. And so what I have here, I have the function, this is f of x equals the square root of x, and this is the equation of a tangent line. And I'm going to write it in functional form. In other words, I'm going to input an x into that line. And you can see right here at 4, that line and that curve look very straight. They almost look like the same thing, don't they? And here's 4.5. You can't tell the difference between the line and the curve, can you? Next page. In fact, I blew it up even closer. Now you can see there's a little gap. This is the tangent line. This is y of t down here, and this is f of x down here. You can see a little bit of gap. And then I really blew it up. And you can definitely see this gap right here, can't you? But if you look at the y values, this is a little bit more than 2.124, and this is a little bit below 2.12. I mean, it's really, really close, isn't it? So our goal in linearization, our goal is to estimate the value of f of x for some x near c when f of x is difficult to compute. Since we cannot compute f of x, we will compute the values of a function t of x. I called it, I think I was looking, when I was reading some materials, t of x stands for tangent. Okay, so in other words, in my head, t of x is the same as y. I'm saying those are the same thing. To approximate f of x, we're doing this. This is the function. This is the tangent line. So really, all I need is c and f, don't I, to come up with the equation of a tangent line. Because if I got f, I can take the derivative of f. All right? Next page. This stands for tangent line. Or tangent function. The linear function whose graph is a tangent line, that is, t of x equals f prime of c minus x of c plus f of c, is called the linearization of f at c. So, notice what I do. Here's my example. I'm trying to figure out what f of 4.5 is. In other words, I'm trying to figure out what the square root of 4.5 is. So x is equal to 4.5. I'm going to use c to be 4. Why? Because in my head, I can take the square root of 4. And 4 is close to 4.5. Another c I could have taken was 9, correct? Why could I have chosen 9? Because I can take the square root of 9 in my head. It's 3, correct? But 9 is a lot 9 is a lot further away than 4 to 4.5. Would you agree? Do you understand my logic there? So now I'm going to come up so the first thing I did is I figured out my c. In my head I figured what f of 4 was. Then I took the derivative. Are you okay where this came from, or should I show you how I got the derivative on this? I'm going to do that. This is the same if f of x is equal to x to the 1/2. I'm going to use the power rule. I'm going to get 1/2 x to the negative 1/2, and that's what that is. So when I plug 4 in there, I took the square root of 4, got 2. 2 times 2 is 4. So that's my slope. So my tangent function looks like this. 1/4 times x minus 4 plus 2. The 2 is from here. The 1/4 is from here. The 4 is that. My x is 4. Yes, ma'am.
Do you want us to write t of x, or can we write y?
I'll let you do either one. I don't care. Okay? They're the same. Whichever makes sense to you. So now what I'm going to do is I'm going to plug 4.5 into there. And I'm going to have 1/4 times 4.5 minus 4 plus 2. That gives me 1/4. 4.5 minus 4 is what? 0.5, right? Can I write that as 1/2? Are you okay with that? Plus 2. My answer is 2 1/8. Or, if people like decimals, 2.125. So, f of 4.5, which is equal to the square root of 4.5, is approximately 2.125. Is it equal to 2.125? The answer is no. But my real answer is really close. So, you have your calculator out. Can you actually, on your machine, figure out the square root of 4.5? What is the square root of 4.5? 2.121. And look what I got using a line. That's pretty good, isn't it? Next page. Okay, so we're going to do this calculator free. It says find the linear approximation for the following if c equals 0. So I'm first going to figure out what f of 0 is. What would be my answer? What is it? 1. Then the next thing I'm going to do is I'm going to figure out what the derivative of f of x is. Well, this means f of x is equal parentheses 1 minus x to the 1/2. So, Cora, are you caught up? Okay. In this form, what's the derivative?
1/2 times 1 minus x. No, to the negative 1/2.
Correct. Would everybody agree? She used the chain rule, didn't she, to get the -1? And so I'm going to have a -1 over 2 times the square root of 1 minus x. Now I'm going to figure out what the slope is at 0. Because c is 0, isn't it? So what would I get? A -1/2. I bet you're able to do that in your head. So now I'm going to, my tangent line is equal to a -1/2 x minus 0 plus 1. Any questions of where those numbers came from? This is f prime of 0. This is c. This is f of 0. Now, and you could write this. That's the same thing, correct? You need more?
Yeah, this is our last one.
I could make some.
Because I don't know how the other groups are doing. But we only got one left.
Can you go find the other group first?
Yeah, you want us to?
Yeah, because I'm streaming right now and you're live. Would you like to say hi to the people out in?
Hi, everyone.
You want to be on the camera?
No, I'm good with that.
Are you good with that? Kayla, you want to be on the camera? Huh?
I'm good.
You good?
Yeah.
Okay,
Stop
just so people know you're real. Because some people out there send me messages saying that I'm not really talking to anybody, that I'm just here by myself, and there's really not a school. Because people, you don't hear anything, and so it's like I've got fake students out there.
Are you guys not talking or anything during class?
Well, what? You can't hear it on the microphone? I gotta fix that. So you can hear that. So it's supposed to be. Maybe we'll hear you. You'll have to go to YouTube and see if you are actually on this thing. Okay. So why don't you do that? I just got a little bit left to do. Okay.
We'll stop back.
Yeah. All right. So what are we going to do now with this? Should I remember we want to do it in our heads, right? This is close to 1, isn't it? Right? So what's x in this case? Is it 0.9? No. What is it? Right? X is equal to 0.1. Why is it 0.1? Yeah.
Because it's 1 minus x. So to get 0.9, you gotta take like 0.1.
Yeah. So it's the equation is f of x is equal to square root of 1 minus x. Okay. And to get close to 0.9, you got x has got to be 0.1, correct? Well, look at this. This right here, this is my function, right? Everybody agree? So really, it's 1 minus x is equal to 0.9, right? Does that make sense now? So that x has got to be 0.1, doesn't it? Right? So that means I'm going to put I'm going to put 0.1 into here. So I'm going to have a negative 0.5, that's what 1/2 is, times 0.1 plus 1. Well, what's that number? Do we know how to multiply that? A negative 0.05 added to 1. What does that give me? 0.95. On your calculator, what is the square root of 0.9? 0.9486. Okay. Well, that's pretty close to 0.95, isn't it? Okay, so now this means 1 minus x equals 0.99, right? So x is going to be what? 0.01. So that means I'm going to put 0.01 into there. So I'm going to have a negative 0.5 plus 0.01 plus 1, and I would get what is my answer. Did I make a mistake here? Oh, not plus, times. Sorry, I did make a mistake. 0.995. Is the square root of 0.99 close to 0.995? It is, isn't it? It's really close. Okay, next page. All right, so it says if f of x, if y equals f of x, where f is a differentiable function, which means I could take the derivative anywhere in the function, the differential d of x is an independent variable. That is, d of x can be the value of any real number. It's the change of x. The differential d of y is defined in terms of d of y by the equation. Isn't this a name of the derivative? Isn't this the name of the derivative? So if I multiply this side by d of x, and I multiply this by d of x, isn't what I input into f prime and d of x my independent variables? And they make dy on that equation. So dy is a dependent variable. It depends on the value of x and d of x. If d of x is a specific value and x is taken to be some specific number in the domain, then the numerical value of dy is determined. To get a better understanding of what a differential represents, look at the diagram from example 1. Label the values of dy dx. So, this right here is our point, correct? This is x, comma, f of x. Why do I know it to be the case? Because it's on the function, isn't it? Right? This right here is x comma t of x because it's on the tangent line. Right here, I have a point C, comma, f of c. It's right here. This has a slope, f prime of c. Right here, how do I want to write this? So I'm going to change this a little bit. F of x minus f of c over x minus c would be the slope of this secant line right here. The limit as x approaches c means this x is moving in this direction, correct? It's headed towards c, which is right there. And f of c equals dy over dx. Well, if you look at this limit, dy dx is changing, isn't it? Pretty soon if I'm here, I have a different secant line. If I'm here, I have a different secant line, correct? If I'm here, I have a different secant line, right? So this right here is the difference between this y value and this y value. And as I move this along closer, these differences get closer and closer, right? Here's my tangent line. This is my secant line. That's what this limit is all about. So what I am saying is that as c moves, and I get dy dx, it's approximating the real slope because as it's getting closer, this is changing and it's approximating that. Now notice dx equals delta x in this point because you're here I am on the curve, it's got the same x value. When I'm here, here's my tangent line, I have the same x value. Here they have the same x value. Here they have the same x value. Here they have the same x value, correct? And what's happening is as I move along the line, dy starts to approximate the real change in y. That's on the function. So this is the justification that we can use to figure out why a linear approximation works. Because this line, this delta y and the change in the tangent line start to become one. That's what I'm trying to say there. So let's take a look at this particular problem. I tell you, it says use a differential to determine this, what I'm going to use is the equation of a tangent line. All right? So first of all, what's f of x in this problem? And we'll go to Jeremiah. In example 2, what's the function? X to the 6th. And it tells you c is equal to 1, correct? Okay, so you'll always know c. So if I plug 1 in there, what do I get? 1. Okay, so what's my derivative? 6x to the 5th. So what's the slope of the tangent line at 1? 6. Everybody agree? Everybody agree? So, Jeremiah, what's the equation of my tangent line?
1 times x minus 1.
What's my slope?
1.
Let's try it again. What's my 6? Okay. Times
X minus 1.
plus what?
Plus
1. Okay. Now, what do you think I'm going to be putting into there? Well, not on this case, because this is x, right? I'm not doing anything to x, right? Remember I had 1 minus x before, right? So what I'm putting in here is just x. I'm going to put in 1.01. So I'm going to have 6 times 1.01 minus 1 plus 1. Okay? What do I get? I get 6 times what? What do you get when you subtract that, Jeremiah? 0.01. Now, notice they call that d of x. And they should have 0.01 right here. They screw up. Okay? Because that's the change, that's the difference between my c, okay, and my x is 0.01. In other words, I have some curve here. Let's say there's my curve. And right here is 1. Right here is 1.01. Well, the difference between them is d of x. That's the change from this x to that x. It's 0.01. So I'm going to plug in, I'm going to take 6 times 0.01 and add 1, and I get what is an answer? 1.06. So I'm going to approximate the next one. What will that look like? Well, into my function, I'm going to put 1.001. And I'm going to, I can skip this part, can't I? Do I know the difference between this and 1? Aren't I going to do 1.001 minus 1? The difference, d of x, the difference between those is what? Ryan's asking. Do you have an idea? What's the difference between this and the number 1? So I'm going to have 6 times 0.001 plus 1. This is what you get when you plug in 1.001 and subtract 1. So what's my answer? Well, it's going to be 1 plus 0.006. That's what my approximation is. One more time, all right? Morgan, what's f of x? x to the 5th. What is c, do you think? C is 2. Do you know why I choose 2? It's the whole number that is closest to 2.001. Okay. What's f of 2? Do you know that? What's 2 to the 5th power? 32. Very good. What's the derivative of f of x? Say it again. Okay, now here's the hard part. What are you going to get when you put 2 into that? What's x to the 4th? Times 5. What? I don't think so, but you're close. What's 6 times 5? What? Did you say 30? What's 5 times 10? What's 50 plus 30? What? 80 is correct. So what's the equation of my tangent line? What? I didn't hear what you said. T of x equals what? My slope is first. 80 times what's my c? 2 plus what? 32. Okay, now I'm going to plug 2.001 in there and subtract 2, correct? Can you do that in your head? So I'm going to get 80 times 0.001. Is that what you said? This right here is d of x. It's the difference between this 2 and this 2.001. That's all it is. Plus 32. Are you able to do that in your head? 0.0. You are doing marvelously. You haven't even touched a calculator. Plus 32. Are you able to do that in your head? 32.08. So 2.001 to the 5th is approximately 32.08. So people with a calculator actually take 2.001 and raise it to the 5th power. How far away are we? Do you have an answer?
Yeah, it's 32.08.
Pretty close, right? And she did not need to take 2.001 times 2.001 times 2.001 times 2.001 times 2.001, did you? The hardest part of that was 16 times 5. See how nice that is? All right. That's it.